Alright guys, in this video I'm going to cover 6.2, which is inverse functions. And before we jump into inverse functions, I want to just take a second and write out the definition of what it means for a function to be one-to-one. So a function is one-to-one, denoted 1-1. If you were to give me any two x values that are not the same, then their corresponding y values are also not the same. So and I've got three different mappings here that I'm going to use to illustrate this. So let's say we have a relationship that takes x1 and sends it to y1 and y2, and then x2 gets sent to y3. Okay, so since this x value is being sent to two different y values, this does not meet the definition of a function. Okay, so it can't be a one-to-one function if it's not a function to begin with. Remember, the definition of a function is for every x value, there's at most one y value. So this does not meet the definition of being a function. Now, if we look at this next one, let's say we have x1 gets sent to y1, x2 gets sent to y1 also, and x3 gets sent to y1. Every single input value is being sent to at most one output value. So this is a function. However, x1 and x2 are not equal to each other, but notice they're being sent to the same y value. So their y values are not equal. Or sorry, their y values are equal, which means that this is not a one-to-one relation. Okay, and then this last one here, if x1 is getting sent to y1, x2 is getting sent to y2, and x3 is getting sent to y3, this is a function. And every single x value is being sent to its own y value, and none of them are sharing a y value. So specifically, this is called a one-to-one function. Okay, so a few things to just kind of pull from this is, for a function to be one-to-one, every x value has a unique y value. So it's not shared with any other one. And the fact that it's not shared means that we have no repeated y values. Remember, repeated x values means it's not a function. Repeated y values means it's not one-to-one. If we satisfy that we have no repeating x values and no repeating y values, then we have a function that is indeed one-to-one. Alright, so that's how we can tell if a function is one-to-one using a mapping. It also, the same logic applies to tables or sets of ordered pairs. Graphically, a function is one-to-one if it passes the horizontal line test. And we usually just denote that with HLT. Okay, so for that, I'm going to just sketch a graph of two functions. So the first function I'm going to graph is f of x equals x squared. And then the second one I'm going to graph is f of x equals x to the third. So we have what's called the vertical line test. The vertical line test says if I can draw a vertical line anywhere and it doesn't cross the graph more than once, then the graph is indeed a function. But the horizontal line test says if I can draw a horizontal line and it crosses the graph more than once, then we say that it fails the horizontal line test, which means that the function is not one-to-one. Okay, and we can see that because if I were to think about this as this is at 2 squared is 4, and then over here we have -2, and -2 squared is also 4. So we see that we have a repeated y value, which means it doesn't match the definition of being a one-to-one function. Now, over here with f of x equals x to the third, no matter where we draw a horizontal line, it only crosses the graph at most one time. Okay, so this we would say passes the horizontal line test, which means that f of x equals x cubed is a one-to-one function. So this whole concept of one-to-one functions is important for where this lesson is leading to, which is inverse functions. And so what it says is if y equals f of x is a one-to-one function, then there exists an inverse function denoted f inverse, such that x equals f inverse of y. So, for example, if we have this mapping x1, x2 is being sent to y1, y2, and the function takes x1, sends it to y1, it takes x2, sends it to y2. This is indeed a function, and since it is a one-to-one function, what that means is there has to exist a inverse function that takes the y values and sends it back to the x value, and this is called the inverse function. So the original function says, give me the input, I will tell you the output. And the inverse function says, if you tell me the output, I can tell you the input that it came from. So, with that said, guys, I want to show you something. We've got f of x equals x to the third power. Which looks something like this. Passes through 0, 0, it passes through 1, 1, it passes through negative 1, negative 1. Now, the inverse function would be, inverse just meaning opposite. The opposite of cubing something is taking the cube root. Okay, so the inverse would be the cubed root of x, which this is a function that we've graphed also in the past. I'm going to graph it on the same graph. It passes through 0, 0, it passes through 1, 1, it passes through negative 1, 1, but instead of being an S shape that goes up and down, it's an S shape that goes side to side. Okay, and this is the graph of the inverse function. Now, what's important to realize from this example is, if I come in here and draw the line, y equals x, the inverse function is a mirror image of the original function across the line y equals x. Okay, so something to make note of is the function f of x and its inverse, f inverse of x, are symmetrical about the line y equals x. So what that means is, if you know what the original function looks like, you can very easily draw the inverse function by just reflecting it across this line. Okay, and so let's do an example of this. So let's say we have, here's an example. Given f of x, sketch f inverse of x. Alright, so, and let's say we're given this graph. So, negative 2, negative 1, negative 1, 0, 2, comma 1. And let's say this is the graph of f of x. If we want to sketch f inverse, what we're going to do is we're just going to come in here, we're going to draw the line y equals x. And then we're just going to draw the mirror image of this. Well, here's what's kind of interesting that happens. This point here, which is at negative 1, 0, is now going to be on the opposite side of the line at 0, negative 1. This point, which is at negative 2, negative 1, is going to be on the opposite side of the line, and it's going to be at negative 1, comma, negative 2. And this point, which was at 2, comma, 1, is going to be on the opposite side of the line at 1, comma, 2. Okay, so really when we sketch the inverse, we simply graph each ordered pair x comma y. Sorry, we simply graph the inverse of each ordered pair x comma y, which is going to be y comma x. So if we want to graph an inverse function, we just take the x and the y values and we switch them in order to create the graph of the inverse function. Now, from here, what I want you to do is look at the domain of f and the range of f. So looking at the f function, we see that the domain is negative 2 to 2. It runs from negative 2 to positive 2. And the range is, it runs from negative 1 to positive 1. Now let's take a look at the domain of the inverse function and the range of the inverse function. So the domain of the inverse function starts at negative 1 and it goes to positive 1. And the range is, it goes down to negative 2 and it goes up to positive 2. Okay, and this should make sense because if we want to graph the inverse function, we just take x and y and switch them. Well, what's that mean in terms of the domain and range? The domain is the set of x, the range is the set of y, and if we take them and switch them, we get the domain and range of the inverse function. Okay, so that's kind of important to maybe make note of. The domain of f of x will always equal the range of f inverse of x, and the range of the original function will always equal the domain of the inverse function. Alright, and then the next thing we're going to cover is how do we verify if two functions are inverses. So verifying inverses. So let's just think about this. If we have x and its corresponding y value, and the function f takes x and sends it to y, and then the inverse function will return that y back to the x. So what that means is f inverse of f of x. So if we apply the original function first and then the inverse function, the answer of that should always be x. Now, also, if we apply the inverse function to an x value and then the original function, we should get x. So if we want to verify two functions are indeed inverses of each other, we have to verify that if we plug one function into the other, it gives us x, and we have to do that in both directions. So as an example here, verify f of x equals 2x plus 3 and f inverse of x equals 1/2 x minus 3 are indeed inverses. And we can see they do look very similar to inverses. Because look, this is 2 times x plus 3, And the opposite of adding 3 is minusing 3, and the opposite of timesing by 2 is timesing by 1/2. So they do indeed appear to be inverses, opposites of each other, but we need to actually verify that. So what we're going to do first is we're going to do f inverse of f of x, which just means we're going to plug the function 2x plus 3 into the inverse function. So 1/2 parentheses x minus 3, and where the x was, we're going to put 2x plus 3. Now, since we just have a subtraction in here, the parentheses is not needed. And then we see that the plus 3 and the minus 3 will cancel, leaving us with half times 2x. And half times 2x does indeed give us x, so that checks. We also need to verify that f of f inverse of x gives us x also. So now in this case, we're going to plug the inverse function into the function 2x plus 3. So 2x plus 3, and then 1/2 times x minus 3. Now, we have 3 multiplications here. 2 times 1/2 times x minus 3. And for example, if I want to do 2 times 3 times 4, I would just do 2 times 3 first, which is 6, and then do 6 times 4 to get 24. Okay, and we're going to do the same thing here. We're going to do 2 times 1/2 first, which just makes 1. So really we just get the x minus 3, and then the plus 3. And then once again, since we're adding, we don't need to need the parentheses, so the minus 3 and the plus 3 cancel, which then gives us just x. So that indeed does check. Alright, and so let's do one more of these. Let's check if f of x equals 1 over x minus 1 and g of x equals 1 over x plus 1 are inverses. Okay, so this one's not as easy as the one we just did above it, but this is saying check to see if they are inverses. So we need to check if f of g of x, if I plug the one function into the other, I get x, and if I plug the other function into the one, I get x. And if neither one of those happen, then that means that they're not inverses. So plugging g of x into f of x is going to be 1 over x plus 1 minus 1. And then that gives us 1 over x, because the plus 1 and minus 1 would cancel. And then we can't divide by a fraction, so we're going to do 1 times the reciprocal, which is x over 1, which does give us just x. So that checks. But then we also need to check g of f of x, which says plug f of x into g. So that's going to be 1 over x minus 1 plus 1. And then same thing, we can't divide by a fraction, so we're going to do 1 times x minus 1 over 1 plus 1. These 1's are irrelevant. We get just x minus 1 plus 1. And since we're adding, we no longer need the parentheses, and the 1's would cancel, which gives us just x. So check if f of x and g of x are inverses. Since these both simplified down to x, f of x and g of x are indeed inverses. Alright, and then the last thing we're going to cover is if you're given a function, how do you find the inverse of the function? Okay, so find the inverse of f of x equals 3x plus 5. Now this is saying we're multiplying by 3 and then we're adding 5. And the inverse means opposite, which means that we should be minusing 5 and then dividing by 3, doing it in the opposite order. Okay, so here's how this is going to work. You're going to, step 1 is replace the function with y. So we're just going to come over here and we're going to easily just rewrite this as y equals 3x plus 5. Step 2 is we're then going to invert x and y, which means we're just going to take x and y and we're going to switch them. Okay, so we're going to invert them. And then step 3 is going to be to solve for y. So now to get this new y, which we'll call this the inverted y, this is going to be the inverted y, we're going to solve for it, which means just get it by itself. So we're going to minus the 5 over, which is going to be x minus 5 equals 3y. Then we're going to divide by 3. So we get y equals x minus 5 all divided by 3, which could be written as 1/3 times x minus 5. And then replace the inverted y with the new inverse function notation. So now that we've solved for the inverted y, we've found the inverted function. So the inverse function is going to be x minus 5 divided by 3. And that should make sense, because if the original function says multiply by 3, then add 5, doing the exact opposite of that would be to subtract 5 first, then divide by 3. Okay? And then so now the last example we're going to do is find the domain and range of f of x equals 2x plus 1 over x minus 1 and its inverse f inverse of x. So let's find the domain and range of this function and the inverse function f inverse of x. Okay, so real quick, going with the function that we have right now, f of x equals 2x plus 1 over x minus 1. We can find its domain using the concept of implied domain. X minus 1 cannot equal 0, which means x cannot equal 1. So in terms of f of x, the domain is going to be negative infinity to 1 and 1 to infinity. Now we have never went over, well, how do you find the range of the function algebraically? The only thing we've done is, well, in order to get the range, what we'd have to do is we have to create the graph, and then we'd use the graph to find the range. We've never gone over that. But we're going to go back to this fact right here. The range of the original function is equal to the domain of the inverse function. And we know how to find the domain of a function algebraically. So if we can find the inverse function and then find its domain using the implied domain concepts, that will give us the range of the original function. Okay, so now we need to find what f inverse of x is. Alright, and it's the same process that we just did up here. Step 1 is going to be to replace f of x with y. So we just write it out in like a standard equation. Y equals 2x plus 1 over x minus 1. Then we're going to invert it, which means that this y is going to become x, and both of these x's are going to become y's. And then now we're going to resolve for y. So first thing we're going to do is we're going to get rid of the fraction. We're going to times the y minus 1 over, which is going to give us xy minus x on the right, or on the left, sorry. And we get just 2y plus 1 on the right. Now since we've got multiple y's, we need to get our y's together. So what I'm going to do is I'm going to add the x over, because it doesn't have a y attached to it, and I'm going to minus this 2y over. So that gives me xy minus 2y equals, on the right side, x plus 1. And then now that these both have a y in them, we can factor out a y. And we get y times x minus 2 equals x plus 1. Divide the x minus 2 over, which gives us y equals x plus 1 over x minus 2. And this is now the inverted function. So now we can say, well, we know what the inverse function is. The inverse function is x plus 1 over x minus 2. And then we can find its implied domain. X minus 2 cannot equal 0, which means x cannot equal 2, which means, so now we know the inverse function's domain is negative infinity to 2 union 2 to infinity. And then once again, we're going to go back to this right here. The range of the original function is equal to the domain of the inverse function. So since the domain of the inverse function is negative infinity to 2, 2 to infinity, that means that the range of the original function is negative infinity to 2, 2 to infinity. And then same here. The domain of the original function tells us the range of the inverse function. So we already knew the domain of the original function was negative infinity to 1 and 1 to infinity. Therefore, the range of the inverse function has to also be that exact set. All right, guys, that gives you enough information to complete the homework set for 6.2. Email me if you have questions. Otherwise, I'll see you guys in our next Zoom meeting.